All right, I want to talk about some special values in R. All right, we have NA for missing values. We have null, and we also have NaN for not a number. So what's the difference between all of these things? Okay, well, NA is used to represent basically missing or unknown values. There is an NA for each type of data. So you have an NA for logical, you have an NA for integers, an NA for character type, NA for double type. Okay, whereas null is basically something, it's a zero length vector, and it's used to represent things that don't exist. Okay, the null is its own data type. Okay, it's used to represent things that don't exist. All right, and then there's also something called NaN. NaN is a numeric value. It is always type double. This is something that in the floating point number representation and specification, there's NaN, and this is used to kind of represent indeterminate values like 0 divided by 0 or negative infinity plus positive infinity. What do you get when you do that? You're going to get NaN. Okay. What's maybe going to throw a few of you off, if you have familiarity with Python, NaN is also used to represent missing values. But R has its own way to represent missing values, and that is NA. Okay, so again, what's kind of this difference between NA and null is, let's say you're storing information about people, and you have columns for the person's name, the person's age, maybe their partner, and then maybe their partner's age. Okay, so let's say we have a person Joe. Okay, we don't know Joe's age, so we are going to enter NA for Joe's age. Because Joe has an age, we just don't know it. Okay, so we use NA for something that exists but we don't know. Okay, Joe, let's say, does not have a partner. And so what we would do is we would enter null for the partner's name and partner's age, because these values don't exist. Okay, if Joe did have a partner and you didn't know the partner's age, then instead of writing null, you would put in NA. Okay, because you might know that the partner exists, you just don't know that person's age, so you would write NA. So NA is used for things that you don't know that do exist, whereas null is kind of basically used to represent things that don't exist. So as far as NA, including NA in an atomic vector or matrix will not change the data type. Okay, internally there is NA and NA, which is the logical NA, and then you have NA integer, NA real, NA character, and these are all kind of how we're going to store a missing value in vectors of different types. Okay, so if you just use NA and you're putting it inside a character vector, then it's going to get coerced into the character NA, so that every element in that character vector remains type character. If you want to check to see if something is NA, you have to use the function isNA. You can't use the equal sign, the equal sign. Normally, to test if two quantities are equal or the same, you use equal, but that's not going to work for NAs. Okay, so if you have NA equal NA, the response to that is going to be NA. Basically, you're saying, like, in this hand I've got a mystery value, and in this hand I got a mystery value, and the question is this value equal to this value? And the answer is you don't know. You don't know if the value in this hand is equal to the value in this hand. So is NA equal to NA? The answer is unknown, so the answer there is NA. But if you just want to know, hey, do we know the value in this hand or is it unknown to us? You just ask is.NA, right? And if it's unknown, you're going to get back true. If it is known, you'll get a false. So null is used to represent the null object. It's its own type. So if you ask type of on null, it's null. To check if something is null, you can ask is.null on null, and you get back true. If you do really anything else, like you ask is the null NA, you're going to get basically a length 0 vector. And the question for is.na, the answer to that question is always a true or false. And so it's going to be logical type. But here we don't have anything. So we're going to have a length 0 logical vector. That's what logical 0 means. It's a length 0 logical vector. Is null a logical value? That's not true. So is logical on null is going to be false. If you try to do any operations with null, you get back 0 length vectors. So if you do null plus false, the plus operator kind of coerces things into a numeric type. So first it will try to convert it into an integer type. And anytime you try to do something with a null, you're going to get back a 0 length vector. So we get integer 0. If you try to include null inside a vector, so I'm going to combine 4, 5, null, and 3, it's basically like including nothing. So the length of this vector is just length 3, 4, 5, 3, and it's as if nothing was really inserted there, okay? And again, you can't check to see if null is equal to null by doing equal equal. You have to ask the question, is.null? Is it null? And you'll get back a response there. We have 0 length atomic vectors for each data type. So you can have, say, a 0 length logical vector. So I'm going to create a 0 length logical vector stored into L. And I can say, hey, what is the length of L? The length of L is 0. But what is its type? The type of L is logical. Is L a missing value? Okay, the question, any answer to an is question is going to be true or false. So the answer to that question is going to be a true false value, but it's length 0 because L is length 0. So we get logical 0. Is it null? It's not null, so that comes back as false. And if you try to combine a length 0 vector with something longer or with something else, basically you're combining nothing with it. And so you're just here, I just get the value true back. Okay, I can do something similar with a length 0 numeric vector, which is going to be type double. Okay, so the length of D is 0. The type of D is double. If I ask, is it NA or is it null, I get a length 0 logical vector, because again, anytime you ask a is question, is dot something, the result of that's going to be true or false. Is it null? That's false. And if you try to combine, look what happens here. I'm going to combine the length 0 double vector with the value true. Okay, so even though D is length 0 and has nothing to it, the fact that it's type double coerces the true into a 1, and so the result of coercing D in true results in the number 1 here. A lot of times you end up with length 0 logical vectors, or length 0 vectors, because you have some kind of criterion and you're trying to subset using that. So here I say I is going to be an integer vector with the values 1, 2, and 3. And then I can have this criterion that says, hey, which of the elements in I are equal to 4? That's a logical vector of length 3, false, false, false. And if I try to subset I using that, basically none of the values in I get returned. So I'm going to get a 0 length vector. Because I itself is integer, I'm going to get a 0 length integer vector. You can also have an empty list. Empty list is a 0 length list, and that is different from a list containing the null object. So here I've got li, which is a 0 length list. I just created lists with nothing inside. And if I ask, hey, what is the length of li? I get 0. That's the length. Okay, I'm going to create another object called li null. This is going to be a list containing the null object. And so if I ask li null, then I have a list, and inside that first element, I have null in it. Okay, so if I ask, hey, what is the length of li null? Its length is actually 1. Okay, here I can say create a list li double, and inside the first element of the list is a 0 length numeric vector. And so if I ask, hey, what is this? Li double is going to be kind of like this. I've got the a list element, but the first thing in the list element is a zero length numeric vector. Okay, what is the length of this list? Also length 1. Right, so that's different from a list that contains nothing, which is a zero length list. Okay, let's talk a little bit about doing some arithmetic with vectors. And one nice thing about R is that a lot of these arithmetic operations are vectorized, and they're very quick. So here I've got a vector x with the values 1, 2, 3. I've got another vector y with the values 100, 200, 300. And you can do x plus y, and these are going to be vectorized. And we're just going to add the first elements together. 1 and 100 give me 101. 2 plus 200 gives you 202. 3 and 300 gives you 303. Similarly, if you do x times y, 1 times 100 is 100. 2 times 200 is 400. And 3 times 300 is 900. And R does this very, very quickly. It is very fast at these vectorized operations. Now, if you have some kind of operation and you have two vectors of different lengths, R will automatically recycle the shorter vector until it matches the length of the longer vector. So here I've got a vector 1, 2, 3, and I'm going to add it to this vector 100, 200, 300, 400, 500, 600. Okay, and so it's going to recycle. First it's going to do the 1 plus 100, 2 plus 200, 3 plus 300, and then it's going to recycle the shorter vector, and it's going to do 1 plus 400, 2 plus 500, and 3 plus 600. Okay, and that's fine. If you have something like this, where you have a length 5 vector, and this is the length 3 vector, R is still going to do the same thing, and it will just kind of throw away the leftover values. So R is going to throw an error. So again, 1, 2, 3 plus 100, 200, 300, 4, 5, and 600. The 1, 2, 3 get assigned to the first thing, and then it kind of recycles around, and you get 4 plus 400 plus 1, 500 plus 2, and 600 plus 3. Okay. If you do this where you have these vectors that are length 3 and length 5, they're not quite compatible. R still allows you to do it, but it throws in a warning, and it says, are you kind of sure you wanted to do this? Because the longer object length is not a multiple of the shorter object length, meaning, if the longer one had 6 elements, then it's, a multiple twice as long as the shorter one. And so kind of the recycling is even, and all of the values get used up the same number of times. Similarly, you can do operations that involve recycling in a matrix, but the recycling for a matrix is always handled column-wise. So here I have this matrix where I have 1, 2, 3, 4, 5, 6 going across the rows, and I created that using rbind, which binds rows together, and I've created this matrix here. Here, if I say m plus x, where x is this vector, 100, 200, 300, you can see it gets applied down the column. So 100 gets added to 1, 200 gets added to 4, 300 gets added to 7, then it recycles around. 100 gets added to 10, and it comes to the next column. 200 gets added to 2, 300 gets added to 5, then recycles around. 100 is added to 8. 200 is added to 11, and basically you get this, and this is probably not what we wanted. Okay, if we wanted to do things column-wise, we have to be a little bit creative, and so this will involve us first transposing the original matrix M so that the values are in columns 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 down the columns. Then I could add x. Adding x here recycles them down the columns. 100 to 200, 300 for that column, 100 to 200, 300 for that column, 100, 200, 300 for that column, and so on and so forth. And then finally, to kind of get it back into the original format, I will transpose that result. So I have take the matrix, transpose it, add x, and then transpose the result. And now we have across the rows 100, 200, 300, then the next row 100, 200, 300, so on and so forth. All right, and so that's how you can kind of work around some of R's, kind of limitations or quirks that, say, adding things down the column, you might not like, but you can kind of work around it by using, say, the transpose function.